Hello, everybody. So this is section 5.5. We're going to do this in one day, and it's systems of inequalities. And an inequality is something that is unequal. So here's one example. Y is less than x plus 3. So what are the solutions to this? There are two variables, so your answer is going to be two numbers, an x and then a y, so an ordered pair. So what are all the solutions that make this inequality true? Well, there are lots of them. 0, 2, for one, if x is 0, then this is 0 plus 3. And if y is 2, well, 2 is less than 3. That's a true statement. But then 0, 1 is a solution, because if x is 0, you have 3 on the right side. And if y is 1, 1 is less than 3. 0, 0 is a solution. 0, negative 10. 1, 3 is a solution. If x is 1, then 1 plus 3 is 4. And when y is 3, 3 is less than 4. 10, 12 is a solution. If x is 10, this becomes 13. And if y is 12, 12 is less than 13. And it just goes on and on and on. So there's a couple of things to notice. One is that there are an infinite amount of solutions. So forget any idea of listing them all. It's completely impossible. So there must be another way to express all solutions to this. And then the big news too is that this is not a function. I hope you recognize that right away. A function of x is defined that every x value is being assigned to one y value. So here, 0 is an x, 0 goes to 2. Well, then 0 goes to 1 also? So right away, it is not a function of x. Here's how we can express all solutions to that inequality, the shaded region. So every ordered pair in this shaded region, which there are literally an infinite amount, it satisfies the inequality. Here's 0, comma 2, here's 0, comma 1, 0, 0, 10, 10, 12 is over here somewhere. It's in the purple section. And notice it has a dashed line because every ordered pair that's on the dashed line won't work. So here is an ordered pair on the dashed line, which is 2, comma 5. X is 2, y is 5. So when x is 2, this becomes 5. And when y is 5, you have the statement 5 is less than 5. And that's not a true statement. 5 is not less than 5. So the dashed line indicates ordered pairs that are not solutions. How do I find all the solutions to this? Remember, we can't list them, but this one, the inequality is different. The y values are greater than or equal to this. But this is a line in mx plus b form. So I've got a y-intercept of negative 1, and the slope being negative 2/5, that's the ratio or the rate of y values compared to x values. So the y values would go down 2 every time I go over 5. So if this were money, you would lose $2 every time you worked for 5 hours. And the ratio, since it's called slope, well, it's called slope, it has a special name because lines are the only thing really that have a constant rate of change. So it doesn't matter where I am on the line, it is always going down 2 over 5. So I know this is on the line, this y-intercept. So from here, I would go down 2 and over 5. I could also work backwards and go up to left 5 and do it again, up to left 5. So you can see you have a line. But this line is different from the other line because this line is going to be a solid line. And it's solid because of that equal sign, because it's greater than or equal to. So first of all, the equal to part. If it were just y equals this, then the line would be the only solution. Any ordered pair that is literally on the line is the solution. But there's also the greater than part. So all the y values that are greater than this line are all the y values up here. Y is in charge of up and down, right? So if y is greater than, then you're going up. So you'd have to shade this area over here. And all this is shaded. All these ordered pairs are a solution to this. And again, not a function. It horrendously fails the vertical line test. No matter where you put a vertical line, you're hitting trillions and trillions of ordered pairs. Not just the ordered pair on this line, but all these ordered pairs are solutions to this. So dashed or solid. If the inequality does not have an equal to sign, then any point on the line or the curve is not a solution, like our first example. So to express that, we used a dashed line or curve. But if the inequality is equal to, so an inequality is a combo, it's equal to and it's either less than or greater than, then the line or curve is solid. And that is communicating that the ordered pairs that are on the line or the curve are solutions. So just to reiterate the point here, this is solid because all the ordered pairs that are on this line are also solutions, just like all these ordered pairs. This line is dashed, so the ordered pairs that are on this line are not solutions, but all the ones that are shaded are. And here is our last example. We have two videos. The second video we'll talk about how to do this on MyMathLab. So I've got a parabola and a line. Well, the parabola, using my transformations, I would go to the right 3 and up 2. And I want to change my mind. I want to go to the left 3 because based on my graph here, I have more room to the left. So I'm going to go to the left 3 and up 2. And that's my vertex, left 3, up 2. But then what else do I have? Well, the way the parabola works, if from the vertex, if you go over 1, you would go up 1. If you go over 2, you would go up 4 because parabolas are the squaring function. So if I go over 1, I go up 1. If I go over 2, I go up 4. If I go over 3, I go up 9. 1, 2, 3, and I go up 9, which is kind of off my chart a little bit. Also, you could just plug in these x values. This x value right here is -2. So if you plug in -2, you add 3, you get 1. 1 squared is 1. 1 plus 2 is 3. So that gives you your y value. But then parabolas are symmetrical on their axis of symmetry, so I can just copy all these to the other side, and I have my parabola. I'm going to do my best to draw this. This is not going to go well. So far, so good. Ooh. That's not too bad. Now, the shading. Every ordered pair that's on the parabola, that satisfies the equal to part. But y is also greater than this. So I would have to shade above this as well. So imagine all this parabola is like a cup holding all this water. So every ordered pair in the shaded region is also a solution. But this is a system. So I have to find ordered pairs that not only satisfy this, but also satisfy this. So before I shade, I'm going to graph my other constraint here. And this one this is a line, has a y-intercept of 5 and a slope of 1/2. So from this y-intercept, I can go up 1 over 2, go up 1 over 2 again. I could go down 1 to the left 2. And then I only needed 2 dots, but I've got 4 there, and I can just connect the dots. Now, what do I shade here? Well, the y values on the line, they're equal to, so anything on the line is good, but they're also less than, so anything below the line. So what is the solution here? It is all the set of ordered pairs that satisfy the line and this parabola. So below the line, but at the same time above the parabola, gives me this section right here. This is the solution to that system. The pairs that are on the ordered, the ordered pairs that are on the line work. The ordered pairs that are on the parabola work. Every ordered pair above the parabola, but simultaneously less than the line, are solutions to both inequalities.